Okay, in this lesson, we're going to solve a system of equations by graphing. So first we need to figure out what it means when we say solve a system. A system of equations, and these are going to be linear equations, are going to be two or more lines. And what we're looking for when we say solve a system is we're going to be looking for where they intersect. So say, for example, if I have a line and it looks like this on a graph, and then I have another line and it looks like that on a graph, what we're looking for is this point right there that is the intersection point. And that point, as you notice, it's on both of the lines. So if we substitute the value of that point, say that point would be 1, 6, then 1, 6 would be true in the equation of the first line and also be true in the equation of the second line. So that's how we actually test to see if a point is a solution, as we plug it into the equations and we see if it's true. Now, what we have is we have several different ways of which these lines can intersect. And one of the ways is that they don't intersect at all. And that would be the case here, where we see that we have parallel lines, and if those lines go on forever, they would never intersect. And so we call this type of intersection of the two lines, we say that that's no solution. And that occurs when the lines are parallel. Here's another type of intersection. It's the second one, and we can see that actually there are two lines here. One of them is right on top of the other. So, and in fact, those two equations produce the same line. In this case, every point would be a solution of both equations. We would say that this one has infinite solutions. Now, the third way in which they can intersect is where they actually cross in one point. And these are the only type of solutions the lines can ever have. And so in this case, these two lines, they cross and intersect right there. This would be the case where the system has one solution. So here's an example that we could have. It should say, determine whether a point is a solution to the system. And how we want to do this is we're just going to plug the point into the equations and see if they are true. So for this one, let's plug the point -2, 3 into both equations. So into the first equation, which is 3x plus 5y equal to 2, let's plug that point in. So we would have 3 times a -2 plus 5 times 3, and we're going to say, is that equal to 2? So 3 times a -2, that's going to be equal to a -6, plus 5 times 3 is 15. Is that equal to 2? So -6 plus 9, that's going to be 9, is equal to 2. Well, that's not true. So right now we know that that point cannot be a solution to the system of equations. Even if that point would be true for this equation right here, it still is not true for this one. So the first one that we tested, and so it still wouldn't be a solution. Actually, I guess for an example is, I'm not going to actually draw the lines out for that. That would be a situation similar to this, where if we had two lines, the point would actually be on one of the lines. Say, if it's true on that, it would satisfy one of the equations, but it's not satisfying the other equation. Okay, let's look at this other one, and let's try it. We'll substitute that point into both equations. So let's try 4x minus 7y is equal to 16. And we're going to substitute a -3, -4 in there. So 4 times a -3 is the x value, minus 7 times a -4, is that equal to 16? So 4 times a -3 is a -12. A -7 times a -4 would be plus 28. Is that equal to 16? And 28 minus 12, that would be 16. is equal to 16. So it checks in that equation. So for this equation right here, it's on that line. Let's try it in the second equation. Plugging a negative 3, negative 4 in, negative 6 times a negative 3 plus a negative 4, is that equal to 14? 16? No, 14 is right. So I have a negative 6 times a negative 3. That is a positive 18 plus a negative 4. Is that equal to 14? So I have 14 equal to 14. That checks. So since the point works in both equations, it is a solution to the system, and it is in fact on both lines. Now, sometimes we're not actually going to be looking for the solutions. We may have the type of a problem that just says determine the type and number of solutions. And so what we're looking for is we're going to be saying, okay, what type? Do we have no solution, infinite solutions, or one solution? And we don't want to graph them, we just want to do that algebraically. And what we need to do is we need to put the equations in slope-intercept form. And what's going to happen is if the lines are going to intersect in one point, well, it doesn't really matter what the y-intercept is if the slopes of the two lines are different. They will eventually cross somewhere. So once we put these in slope-intercept form, if we see that the slopes are different, we can say that that system of equations has one solution. If the lines are parallel, they will have the same y-intercept and the same slope. They'll have different y-intercepts, but the same slope. So in this case, we could see that these two lines are going to cross the y-axis at different places, but they have the same slope. So no solutions. If we find out that they have the same slope but different y-intercepts, then they are going to be parallel and have no solution. Now for infinite solutions, you can imagine that case, that's where they're the same line. So if I have a line, and then I have another line that falls right on top of it, those will have the same y-intercept and the same slope. So let's try one of these. So I want to take the equations and put them in slope-intercept form. So if I have a negative 2x plus y is equal to 1, now let's put it in slope-intercept form. So we'll move the negative 2x to the other side. We'll have y is equal to 2x plus 1. Let's work with the second equation. Negative 4x plus 2y is equal to negative 8. So let's move the 4x over. So I'd have 2y is equal to 4x minus 8. Dividing both sides by this 2 that's with the y, we would have y is equal to 2x minus 4. So what we see is the lines do indeed have the same slope, 2 and 2, but they have different y-intercepts, so these lines would be parallel, they would never cross, and this would be a no solution. Okay, let's look at the next one. So 4x minus y is equal to a negative 3. Negative y is equal to a negative 4x minus 3. And now let's get the negative off the y. So y is equal to 4x plus 3. Working on the second line, 2x minus y is equal to 1. Y is equal to, move the 2x over, a minus 2x plus 1. And now let's get rid of the negative on the y. So we have y is equal to 2x minus 1. Notice that these lines have different slopes, so they will cross someplace. This would be a case where they have one solution. Let's look at the last line. So we have 5x minus y is equal to 2. Negative y is equal to a minus 5x plus 2. Getting rid of the negative on the y, y is equal to 5x minus 2. For the second equation, let's move the 10x over. Now let's divide both sides by 2. We can see that they have the same slope, same y-intercepts, so this would be infinite solutions. In fact, let's see if we could have detected that at the start. Look at how these equations are. You can see that if what I'd actually do is take this first equation and multiply it by -2, the whole equation, that would end up giving me the second one. So -2 times 5x is a -10x. -2 times a -y is a +2y. A -2 times a 2 is a -4. So if we're going to have a situation where they have infinite solutions, what's going to really happen is one equation is going to be a multiple of the other equation. If we just take one equation, multiply it by some number, that it's going to equal the other one, and that's also going to tell us that they are infinite. Okay, so now what we're going to do is we're going to actually solve a system by graphing them. And a couple things, comments on this is obviously when we graph, we're not going to have necessarily really accurate solutions. So we always, if we were looking for an accurate solution, we really want to solve them algebraically. But the graphs, when we graph them, gives us a good idea how the lines intersect. So sometimes it's a good idea to go ahead and graph the intersections in addition to solving it algebraically. So let's go ahead and graph this. And you're going to have to use a ruler. Now I don't have one, and when it touches the screen, since this is a tablet PC, I'll have to draw this by hand, and so I may not get a good accurate solutions, but you're going to get an idea of how to do it. Also, it's always a good idea to test the point when you're done to make sure that it works in the equation. Once again, both one of them would have to be true. So let's go ahead and graph this. I'm going to use the intercept method. So if I take a look at the first line, what it's going to be is if I look at for the x-intercept, the y value would be 0. I would get the x-intercept would occur at the point 3, 0. The y-intercept would be where x is 0, and the y-intercept would be at 0, 3. So let's go ahead and put those on there. 3, 0, 0, 3. And let me try to draw a line on there that's reasonably good. Okay, let's try the next one. Once again, I'm going to use the intercept method. So if I set y equal to 0, x would be equal to 4 over 2. That would be 2, 0. And if I set the x coordinate equal to 0, y would be equal to 4. So those are my two intercepts. So I have x at 2, 0, y at 0, 4. And let's try to draw a line through that. And you can see that it's not real accurate where it crosses. I'm going to suspect that actually if I would have had a ruler that I could have got these lines to cross at this point right here. So it looks to me like maybe the point that they cross is 1, 2. And what we would want to do is we'd substitute that back into these equations and see if it's true. So in the first equation, x plus y equal to 3, 1 plus 2 equal to 3. Yep, works in that one. Let's try the next equation, 2x plus 3y equal to 4. Oops, not 3y. 2x plus y equal to 4. And let's plug the 0.12 in there. 2 times 1 plus 2 equal to 4. 2 plus 2 equal to 4. Yeah, check. So graphically my point would be 1, 2 as the intersection point. Okay, let's try this one. And once again, I'm going to do the x and y intercepts. So I have x minus y is a -4. So if I set y equal to 0, I have the x-intercept at a -4, 0. if I set the x value equal to 0, I get y is equal to 4. So x is a negative 4, 0, and y is 0, 4. Let's do the next one. So I have the x value of the intercept would be equal to 5. The y value of the intercept, setting the x equal to 0, would be a negative 5. So x is equal to 5, negative 5. Not very good lines, but they're parallel. And so this set graphically would be no solution. And that's it.